Let's have a look at practice question set number 23. We'll skip question number 1 right now and go straight to question number 2. We'll do the easy one first and then come back to the really, really tough one. Number 2, the way that I see it, there's 2 ways to do this question. There's the mathematical way. We can calculate something and then determine the attributes of the image based on some mathematics, or we can just think back to our ray diagrams and the patterns that we saw in the ray diagrams, either redraw a ray diagram or remember the patterns, and we should be able to get the attributes that way. First way I'm going to do it is mathematically. We have an object placed 35 centimeters in front of a diverging lens. It's a diverging lens. Draw attention to that, right? Diverging lens means that? It means that it's a concave lens, yeah. I don't like using the words concave and convex so much. I use them because we have to be prepared to see that on an exam. Okay, but I would prefer to use the terms converging and diverging. If we've got the terms diverging and converging used on the exam or on the question, great. Okay, that's the way I'd like it. Because I think that they explain more, right? Diverging tells us that rays diverge from a focal point, which tells us that it's a negative focal point, right? That means that this is negative 20 as opposed to 20. The object is placed 35 centimeters in front of it. Let's find the image distance. We're going to say 1 over f is equal to 1 over dO plus 1 over di. The focal length is negative 20, so make sure you include that negative 20 if you're doing it mathematically. The object distance is 35 plus 1 over di. We solve for the image distance here, and it works out to be negative 12.73 centimeters. Okay? The fact that it's negative 12.73 centimeters tells us what? The fact that it's negative di tells us what? Remember that table that we did? F, dO, and di, the sign of it, positive or negative, is based on real or virtual. HI and HO is based on upright or inverted, right? So the first 3 variables, the one that come from that first equation, are based on real or virtual. This is a negative di, so that means it's a virtual image. Okay, that narrows it down to either C or D. Now, how do we determine whether it's larger or smaller? We could take a look at the next equation. M is equal to negative di over dO. And we don't actually need to solve this. di is negative 12, so negative 12.73 over dO is 35. We're going to get a number that's bigger than 1 or smaller than 1 there? Smaller than 1, that means that the image is smaller. So the answer would be D for this one, right? Now, we also know that the image would be right side up here, right? Because we get a positive magnification, although we're not asked that in this case. Yeah, Danielle?
Here's how you know, like, right off the bat that it's a negative focal length.
We know that it's a negative focal length because it's a diverging lens. Anytime you have a diverging lens or a diverging mirror, for that matter, we learned about mirrors yesterday, right? Diverging goes with a negative focal point. Okay, why? Well, because the focal point, if you have a diverging lens or mirror, the rays don't actually converge at the focal point. If you have a diverging lens, right, this is your focal point right here, the rays diverge away from the focal point. So that would be a virtual focal point. Not a real focal point, but a virtual focal point. The rays don't really converge there. If we have a diverging mirror, the focal point is over here. The rays diverge away from that focal point. So again, they don't really converge there. They diverge away from it. That makes it a virtual focal point. And remember that F, dO, and di, the sign of it is based on real or virtual. So if it's a virtual focal point, then the focal point is going to be a negative value. Right? Yep, Braden? Yeah, absolutely. It leads me into the next way of doing it. Remember I said at the beginning there's 2 ways of looking at this, the ray diagram and the math. This is the math way, works perfectly. If you remember the ray diagrams, or you remember the patterns, or you sketch a ray diagram, whatever you want to do, in the end, diverging lenses and diverging mirrors both produce the same images, and they're always going to be virtual, they're always going to be upright, and they're always going to be smaller than the object is. So Absolutely. If you remember that, absolutely save yourself the bother of doing the math. Now, having said that, we've talked about things like this before, right? I would say that, you got 6 hours to do that exam, right? Like, we don't want to take 6 hours to do the exam. Like, we do not want to take 6 hours. My son this morning, as he goes to write his PAT, I said, make sure you take all the time you have. He said, Dad, I got 5 hours. So I said, well, okay, don't take all the time you have. You don't want to take 5 hours to do an English PAT in grade 9. You don't want to take 6 hours to do this exam. But you have time, right? So if you think of it your way, using the ray diagram, you're like, okay, I'm pretty sure I'm right. Okay, all right, good. Bubble that in as your answer. And then when you're done, go back and try to do things a different way, right? Like, try to do things the mathematical way the second time around. And if they agree with each other, then like, you get a pretty darn good chance of being correct there. But I would leave doing it the second way until the end. Okay, you don't want to do everything 2 different ways the first time through, because then you're going to be in that 5-6 hour range if you start, or potentially at least if you start doing that way. Yep.
So is the image distance negative because it's a virtual image?
Well, the image distance mathematically works out to be negative, right? And remember that, again, in that table, the first 3 variables in that table, which are f, do, and di, the sign of those are all based on real or virtual. F is positive if it's a real focal point, which comes from converging. Do is positive if it's a real object, and it's always real for us. Di is positive if it's a real image. Well, this came out to be negative, so that must mean it's a virtual image. Hey, does that make sense?
What would a virtual image look like? I can't really...
Well, the virtual image comes from having those dotted lines intersecting.
Yeah.
So we have, of the 10 ray diagrams for lenses, we have 6 of them, we have 3 of them that are real, 1 that produces no image, and 6 that produce a virtual image. So when we have, let's look at one that produces a real image first, okay? So let's say we have a converging lens, or we could have a converging mirror as well, but we're dealing with lenses here right now. Converging lens, here's the focal point, here's 2f, okay, here's f and 2f on the other side, just as spacers. Okay, we have an object over here. The first ray is going to go parallel down to the focal point. Second ray is going to go down through the optical center, like this. Okay, that produces an image right here, which is upside down, smaller, and real, because solid lines intersected. Okay? Solid lines intersect, it's a real image. That means it could be projected onto a screen if we so choose to put a screen there. Okay? Doesn't mean we have to. Right? We could just stand right here and look into the lens and still see the image. We don't need a screen, it's just that we could have a screen there if we wanted to. Now, that's as opposed to something like this. Well, let's have a converging lens again. Diverging lenses always produce a virtual image, but let's see a converging lens that produces a virtual image. Here's f, 2f, f, 2f on the other side. Here's our object this time. First ray parallel down through the focal point. Second ray down through the optical center. They don't converge over here, so we extend them backwards. They converge back here. It's the dotted lines that intersect, which means that it must be a virtual image. We could not project it onto a screen.
So meaning like you couldn't see it?
You couldn't see it on a screen. Like right now, you're literally looking at what I'm doing on a screen, right? It's being projected from this projector onto a screen. Okay, that's a real image. Okay, if it's a virtual image, you can see it, but not on a screen. You'd have to physically look in the lens to see it, like you do a magnifying glass. Okay? When you look at the image from a magnifying glass, you're not projecting it onto a screen like you are the stuff from this LCD projector, right? You're looking in the lens to see it. Okay? You have to do that for a virtual image. Whereas a real image, you can put it on the screen like we have here. Okay? Does that make some sense? Okay, good. Keep asking those questions, guys. Those are important, right? Not just the mathematical stuff, but the understanding stuff like that. Okay, let's take a look at question number 1 now, which is the real challenge question here. It says, at what distance above this page would a convex magnifying lens, convex, concave, really what do we want to call this? Converging, right? Converging magnifying lens. That means if it's converging lens or mirror, the focal point is, okay, positive. So we don't need to worry about this one because it's listed as positive on our page. Where does it have to be held for the letters to appear upright and 3 times as tall? We're given the focal length is 10 centimeters, and we're given the magnification is 3. What are we looking for? At what distance above this page would you have to hold it so that the letters would appear 3 times as an image, 3 times as big? No, we're not looking for the image distance. We're looking for the object distance, right? The page is the object, right? The letters on the page are the object that we're trying to magnify to be 3 times, right? Where do you need to place that object to produce an image that's 3 times as big? Well, we only have 2 equations, so try one of them. 1 over f is equal to 1 over do plus 1 over di. 1 over 10 is, oh, that's not going to help me, is it? 1 over do plus 1 over di. All right. Okay, that's not going to help me much. That's okay. What's happened since the beginning of Physics 20 when we try an equation we have too many unknowns? Try another one. Like as long as you're using a valid one, right? Yeah?
I have a question.
Yeah, go ahead.
If it says the image of the letters.
Let's try the other equation here. M is equal to, well, hi over ho, but we don't know anything about that, right? So let's go negative di over do. We don't know much about that either, except that we're looking for do. M is 3 equals negative di over, all right, that's not much help either, is it? What do you see here right now, though? Oh, come on, you math people. You guys are all math people. Don't lie. I got 2 equations here, and I have, Jake? Yeah, I've got 2 equations, and I've got the same 2 unknowns in both of those equations. What I'm going to do here is say di is equal to negative 3 do. And then I'm going to take this value of di and sub it into here. So it becomes 1 over 10 equals 1 over do plus 1 over negative 3 do. Do you see what I've done there? Now, Jake, why did I not rearrange that to solve for to solve for do? Well, because then I would have got, I could have done that and subbed it into here, but then I would have ended up solving for di in this equation, and I'm looking for do, right? All right, so now it's 1 equation, 1 unknown. It's just, like, you got to be good with fractions for this, right? Let's change this around a little bit. Let's say 1 over 10 is equal to 1 over do minus 1 over 3 do. Is that the same thing? Is that the same thing? Yeah, absolutely it is. All right, now, we have 1 over do minus 1 over 3 do. How do you solve for do there? How do you add fractions or subtract fractions? Common denominator, right? So this is, we're going to say 1 over 10 is equal to 3 over 3 do minus 1 over 3 do. Does that make sense? 3 over 3 is the same as 1 over 1, right? That becomes 2 over 3 do. So we've got 1 over 10 is equal to 2 over 3 do. This goes up by multiplying. This goes up by multiplying. And you solve for do, and it works out to be, look at that, 6.67 centimeters. So my answer for that is B. Isn't that a good question? Not really, actually. I'm not really a big fan of it, but I gave it to you because it's a question. But I gave it to you as a practice question because it is so challenging as opposed to a test question.